Okay, so any other questions? As I just said, um, please do not leave before I take the roll. I usually take the roll at the end of class. If you're not sure, just check with me. And I'll just uh, post the link for the first class video on YouTube. If you missed the first class, just click on the link. You can watch it. Any other questions before I start? Okay, if no question, then we just start the first chapter. Okay, the first chapter is the introduction to differential equations. We just, introduce some terminologies, some definitions. So the first section of chapter 1 is definitions and terminology. So this course is called the applied differential equation. So we want to know what it means by a differential equation. So the definition of a differential equation is an equation containing the derivatives of one or more unknown functions, which we also call dependent variables. This is the function we need to solve with respect to one or more independent variables. It's said to be a differential equation, or DE by abbreviation. So in a differential equation, you have an equation of two variables at least. Okay, one is the independent variable, and the other is the function. So we can call the independent variable x, for example, and call the dependent variable or the function y. So we want to solve for y in this equation, but the equation contains the derivatives of y. So we need to solve y from derivative of y. All right. And it has at least, two variables, x and y. Okay. So that's the general differential equation. And then we have two types of differential equations. One is called ordinary differential equation. If a differential equation contains only ordinary differential derivatives of one or more unknown functions, or y, with respect to a single independent variable, x, it is said to be an ordinary differential equation. So we only have one independent variable, x. So then we only have ordinary derivatives, dy over dx, or y prime, or y double prime, But you only have one independent variable. So that's called a ODE, or ordinary differential equation. If an equation involving partial derivatives of one or more unknown functions of two or more independent variables, okay, this should be of instead of or. And this equation is called the partial differential equation. So in partial differential equations, you have two or more independent variables. So that's why you got the partial derivatives. So in a partial differential equation, or PDE, you will have partial derivatives of functions. That means you have more than one independent variables. I don't know if you took Cal 3 or not. In Cal 3, partial derivatives or discussed or covered. If you have not taken
3R kill.
Cal 3, what is that? You did? You took a part Cal 3? Then you know what it means by partial derivatives. So a differential equation involving partial derivatives is called the partial differential equation. Okay, it's that simple. But it doesn't matter. This is just a terminology. In this course, we're not going to discuss anything about partial differential equations. Okay, just make sure you know when you see some literature, you know what it means. Any questions about definitions? Let's go to the next page. So these are some examples of ordinary differential equations, or ODE. So there are 3 equations here. Each of them involves the derivatives of some dependent variable. In the first equation, for example, we got dy over dx plus 5y equal to e to the x. Okay, so x is the independent variable. Okay, now y is the dependent variable or the function we need to solve. So our task is to solve for y from this equation. So the solution of the differential equation should be a function. So y is a function of x. That's why you take the derivative of y with respect to x. And we need to solve for y from this equation. So we want to know what exactly y is in terms of x. Okay. So in the second example, we have another differential equation or ordinary differential equation. This time we got the second derivatives. Okay. So we got d2y over dx2 minus dy over dx plus 6y equal to 0. So this is second order. It's called the second order. You got the second derivatives. But again, you only have one independent variable, x. Okay. And we need to solve for y in terms of x from this equation again. So y is a function we need to solve from this equation. In the third example, this time we have 2 dependent variables, x and y both. There are functions of t. So in here, t is the independent variable. Both x and y are functions. So we need to solve for x and y from this equation. Okay. In terms of t. So all of those are ordinary differential equations because we only have one independent variable. Clear? Any questions? So then these are some examples for ordinary differential equations. So how about the partial differential equations? Okay, so the following 3 examples are partial differential equations. You can see all of those equations involve partial derivatives of some dependent variable or function with respect to some variables x, y, or t, whatever they are. For example, in the first equation, we have delta 2u over delta x2 plus delta 2y over delta y2 equal to 0. So this time we have 2 independent variables. See, so that's the difference. You have more than one independent variable in partial differential equations. So then you get the partial derivatives. You have to specify when you take the derivative, you have to specify the derivative of a function you respect to x or y. So then you get the partial derivatives. So this is second order, you get the second derivatives. or second partial derivatives with respect to x and y. So this is a partial differential equation. In the second equation, similarly, we got the two independent variables, x and t, both are independent variables. And again, we only have one dependent variable, u, and we have all the partial derivatives with respect to x and t. Again, we got the second partial derivatives and the first order partial derivatives. But anyway, this is a partial differential equation. In the third example, this time we got two independent variables, x and y, but we also got two dependent variables, u and v. Those are the functions. U and v are functions of x and y. Okay. So again, this is the partial differential equation. First order, we have only first partial derivative. All right. So you can see, in partial differential equations, you have more than one independent variable. It can be x or y or t, whatever you call it. So that's the difference. Any questions at this point about the definitions? This is pretty straightforward, I think. Okay. The next thing is the order of a differential equation. So what's the order of a differential equation? Is the order of the highest derivative in the equation. What it means is, the order of the highest derivatives, it means the highest derivative. Okay, so for example, the following equation or differential equation is of second order. Okay, so this equation has d2y over dx2 plus 5 times dy over dx cubed minus 4y equal to e to the x. So this is the ordinary differential equation because we only have one independent variable x. It is second order because the highest derivative is 2, or second derivative. It's not 3, okay? Don't be fooled by this power 3 of dy over dx. That's not a derivative, that's just the power. The derivative, the highest order of derivative is 2. So, good. You got a question? Does anybody have any questions? Can you hear me?
Yes, sir. Yes. We can hear you.
Is it good? Everything's good?
Yes, sir.
Yeah.
Okay.
Well, let me. I have a question since I'm already here.
Yeah.
Are these PowerPoints going to be on Blackboard, or are you only recording them for the YouTube videos?
I can put them in Blackboard in the content folder.
Yes, sir.
Yeah, I'm also recording the video in YouTube, and you can if you want to review the video, you can send me an email. I can send the link. All right. Any other questions?
Is it possible you could send the link to your channel in the chat here?
In the channel, what do you mean?
Like the YouTube channel that you're posting the videos on, is it possible if you could send that link to the chat so that we can watch the YouTube videos?
Yeah, I can post the channel or the link next time for today's class. It takes some time to process it, but it will not be today. It will be next time. Would that work for you? Or if you want, you can send me emails. I'll try to process it as soon as possible after the class today. Does that work?
Yes, sir.
Okay. Somebody just posted some channel. What is that?
That's your channel.
Oh, that's my channel?
Yeah, I just posted the link.
Oh, okay. All right. Yeah. Okay, that's good. Thank you. Any other questions? Anything you want to share with us? Okay, so the next thing it's called the nth order ordinary differential equation in one dependent variable. Okay, so we talk about the order of differential equation. That means the highest derivative. So in this equation, you know, we got some function big F. It is a function of the independent variable x. We only have one independent variable in ordinary differential equation. Remember? And then we get a dependent variable y. So this equation only has two variables, independent variable x and dependent variable y, or function y. But it also involves all the derivatives of y from the first derivative to the nth derivative. So this is the differential equations involving all the derivatives of y up to nth derivative. Okay, so that's a nth order ordinary differential equation in one dependent variable in the general form. This is a function big F can be in any form. So in general, we just write this big F of those you know, x, y, y prime up to y nth derivative equal to 0. So you can always write the nth order ordinary differential equation in one dependent variable in this form. Okay. So then we have different cases for this equation. So one, you know, example is linear differential equations. So what it means by linear differential equations, a nth order ordinary differential equation is said to be linear if the function big F on the left is a linear in y prime up to y to the nth derivative. Okay, so this function f is a linear function of y prime, you know, y double prime up to y to the nth derivative. Okay, so more explicitly, this equation will be able to be written as this form. Okay, so you can see we got a bunch of terms. We usually start the term of the highest derivative y, and then followed by the next derivative -1 derivative y, and so on, and then down to y prime and y, and then we got may have some form of x only without the y. So you can see in all of those terms, the derivatives of y, you know, either y to the nth derivative or -1 derivative or y prime or any derivatives of y or y itself, they are linear in this equation. We don't have square of nth derivative y or cube, or you know, for any of those derivatives, we don't have any powers more than 1. All of the powers of those derivatives are 1. Okay, including y itself. So this is called a linear. When we say linear, we mean, you know, those derivatives, you know, has power 1. So then we got constants, a sub n -1, and so on to a sub 1. Those are constants. We call them coefficients. Okay, and a sub 0 is also a constant. And then we got some function of x. Remember, y is the function or dependent variable that we need to solve from this differential equation, and x is the independent variable. So this is a linear differential equation of nth order. Any questions? Is it clear? So we're going to see some examples, Okay, let's just do one more definition before we do the examples. So let's talk about the solution. What it means by a solution of a differential equation. Obviously, when we have an equation and we want to solve for it, and the solution of a differential equation, it will be a function y, as I said before. So the formal definition will be in the following: any function phi or phi defined on the interval I and possessing at least n derivatives that are continuous on I. Okay, you don't have to focus on those wording in here. In mathematics, we always express terms very strictly. That's why we have so many words in the definition. So we got a function phi. It has nth derivatives, and the derivatives of the function phi are continuous. Okay, so that's what it means in here. Which, when substituted into an nth order ordinary differential equation, reduces the equation to an identity. It's said to be a solution of the equation on the interval. So basically, you're trying to solve a differential equation, nth order ordinary differential equation. So you have all the derivatives of phi or y up to n. Okay, so nth derivative in this equation. Then you try to solve this differential equation, and you get some solution as function. We call it phi, and that's called the solution or a solution of the equation. Okay, and in the whole course, we're going to discuss the methods or strategies to solve different types of differential equations. We have different methods for different types of differential equations, and it turns out it is very challenging to solve differential equations. And we're going to discuss those methods one by one. Okay, so let's just give some examples of solutions or differential equations. So in this example, we need to verify that the indicated function is a solution of the given differential equation on the interval from negative infinity to positive infinity. That means, we're trying to verify that the function given in the problem is a solution to the differential equation, and this solution is valid for x from negative infinity to positive for all values of x. Okay. So what is the differential equation? We got the first order dy dx, and we only have first derivative in this equation. So that's first order. And is it linear? No, it's not. Dy of dx is linear because the power of that is 1, but on the right hand side we got the y to the half. So we got the power of y half. So that's not linear. Okay. Remember, in order for the differential equation to be linear, then all the powers of either both derivatives and the y itself have to be linear or 1. Okay, so this is not a linear. It is first order but not linear. So this is the differential equation. Y is the function or dependent variable we need to solve, and x is the independent variable. And the indicated function, so that's the equation we have, and then indicated function is y equal to 1 over 16x to the 4th. And we need to verify this function is a solution to the differential equation. So what we need to do is actually to, if you substitute this function y equal to 1 over 16 to the fourth into the differential equation, the equation should hold. That's the problem. That's what it means in this problem. So what you do is just plug in, y equal to 1 over 16 to the 4 into the equation on both sides and see if the equation holds. Okay. Does anybody have any questions? Okay, if not, then it's excuse me.
Yes, sir. I had a question.
Yeah.
I was going to ask you if it was possible if you could work this problem. I know that you have it detailed like right below it, but is it possible if you could work this on a board so that we could see it, like all the steps going through this problem?
I'm trying to write down all the steps in the slides. You can see, it pretty much detailed. I was trying to work on the iPad or something before, but it's not very convenient for me to write down things without the board, because we don't have the board. So what? I was trying to work on that way before, but it was not very good. People didn't still not quite understand it that way. So let me just try to explain this step by step. If you have any questions, just ask me. Okay, so what we need to do is to plug in this function y equal to 1 over 16x to the fourth into the equation, both on the left and on the right, and see what we get. So on the left of the equation, if we plug in this function, so what we need to do is just take the derivative. The left side is the derivative of the function, right? dy over dx. Sometimes we use different notations. You can use dy over dx or prime to denote that is the derivative of the function. So we need to take the derivative of this function. So this is the power function. The rule we use is the power rule. And you can take out 1 over 16 to the outside. And then you use the power rule to find the derivative of x to the fourth. So the power rule says you're going to put 4 down in the front and then subtract 1 from the exponent. So 4 minus 1 is 3. So we get 4 times x cubed. And then 1 over 16 times 4, if you just reduce it, you get 1 over 4. So that's the left side of the differential equation we obtained, 1 over 4x cubed. Now let's see what we get on the right. So again, you just plug in 1 over 16x fourth for y and see what do we have. So x times y to the 1/2. So if we plug in 1 over 16 to the x fourth for y, then we get x times 1 over 16x fourth to the 1/2, right? So how do you take the 1/2 power of the inside? You just take the 1/2 power of each part. So we still have x in the front, and then we take the 1/2 power of 1 over 16 and the 1/2 power x to the 4. 1 to the 1/2 power is the square root, remember? So 1 over 16, take the square root, you get 1 over 4, remember? You just take the square root of 1 and 16 separately, so you get a 1 over 4. So the square root of 16 is 4 in the denominator. And then how do you take the half the power of 4, x to the 4th? You just use the rule for the powers or exponents, multiply 4.5. Okay, that's what it works. So 4 times half is 2. Okay, so the x times 1 over 4 times x squared. And then you can combine x and x squared. You know, x has the power 1 in here, and then you get x squared. When you multiply them, you just add the exponents. 1 plus 2 is 3. So we get x cubed, and then we have 1/4 in the front. So that's the right-hand side. Okay, so we got 1 over 4x cubed, and we already got 1 over 4x cubed on the left. So you can see the left side and the right-hand side are the same. So, so we already verified that the function y equal to 1 over 16 x to the 4th satisfies the differential equation, because when we plug in this function into the differential equation, the equation holds. Does it make sense?
Yes, sir. This makes sense.
It does or does not?
Yes, sir. It does.
Okay. Okay. All right. Okay. Good. So let's just do another example. This time we need to verify, you know, another differential equation with some other functions. So verify that the indicator function is a solution of the given differential equation on the interval from negative infinity to positive. Again, we get same kind of problem. And again, this negative infinity to positive infinity of x means the solution is valid for all values of x, but you don't have to worry about that too much at this point. So the equation we get this time is second order. We got the second derivative of y. See, that's the highest derivative we got. So that's the second order, and it's linear because each term in this equation, y double prime, y prime, y, all of them are linear. They have power 1 for each term. So this is y double prime minus 2y prime plus y equal to 0. That's the equation. And the function we have is y equal to x times e to the x. So we need to verify this function satisfies this differential equation. So again, you just plug in the function x times e to the x for y into the equation and see if the equation holds or not. So we need to do a little more work this time because this is the second order differential equation. We need to, you know, obviously take the first derivative and the second derivative. Okay. So let's just start from the first derivative. So we need to find the derivative of y or y prime, you know. So when you take the derivative of x times e to the x, so if you still remember how to find the derivative functions, then the rule we're going to use here is the product rule, because we have the product of two functions, namely x and e to the x. Those are the two functions in this problem. Okay, so we have to use the product rule. By the way, sometimes people always ask me, oh, how do I know which rule to use when we take the derivative? It really depends on the problem. If the problem has a product of two functions or more functions, then you have to use the product rule when you take the derivative. If the function itself is a quotient of two functions, for example, then you have to use the quotient rule. So the way the rule to use depends on the problem itself. That's why we have so many rules that apply to different problems. You got a question? Any questions? Okay, for this problem, we got the x times e to the x. So obviously that's a product of two functions. You can call them f and g. So we have to use the product rule. So what's the product rule? The product rule says the derivative of a product of two functions is equal to the derivative of the first function times the second function plus the first function times the derivative of the second function. Okay, that's the product rule if you still remember that. So we have to take the derivative of x in the first place times e to the x, and then plus x times the derivative of e to the x. Okay, so the derivative of x is 1, and the derivative of e to the x, just e to the x itself. Okay, those are the basic rules in differentiation. So 1 times e to the x, just e to the x, and we got another term plus x times e to the x. All right, so that's the first derivative of y. And we still need to take the derivative of y prime to get the second derivative. Remember, the second derivative means you take the derivative of the derivative. So the derivative of y is e to the x plus x times e to the x. And we need to take the derivative of that, okay? So then you just do it term by term. So we have the derivative of e to the x plus the derivative of x times e to the x. Okay, again, the derivative of e to the x is just the e to the x itself. And the derivative of x times e to the x, we already did the, on the first step, see? And that's e to the x plus x times e to the x. So we don't have to repeat again. We just copy down the result. So we got e to the x plus x times e to the x. And you combine the 2 e to the x, you get a 2 times e to the x. So we get the 2 times e to the x plus x times e to the x. All right. So this is the second derivative. Then we just plug in those results into the equation to see what happens. So on the left of the equation, we get the y double prime minus 2y prime plus y. Y double prime is just the 2e to the x plus x times e to the x. And the y prime is e to the x plus x times e to the x. So minus 2 times that. And the plus y, so y is x times e to the x, okay? So then we just, combine those terms. So you just distribute the negative 2 in here. So we got negative 2 e to the x minus 2 times x e to the x, and copy down all the other terms. And then you can see we got a bunch of terms that we canceled. So we get 2 times e to the x minus 2 times e to the x. So they cancel completely. And then we got I'm sorry. And then we got x e to the x minus 2x e to the x plus x e to the x. So again, if you combine x e to the x plus x e to the x, you get a 2x e to the x, and that will cancel this negative 2x ex completely. So everything's canceled. So at the end we got 0. So so that's what happens on the right. So that means the equation holds for this function. So we verify that this function x times e to the x satisfies this equation. So it is a solution to the equation. Good. Any questions about this example? Does anybody have any questions so far? We're going to stop here today, and we're going to continue next time on Friday, on this section. Any questions?
No, sir.
Okay. Okay, I'm going to process the video and you know, next time hopefully I can give you the link. So let me just take the row and then you can leave. Okay. Just 1 second. So I'm going to just stop the share and take the row. Let's see. So we got a lot of people in here. So I guess I just take the picture now. So I'm going to stop the recording.